when you look at a particle like this, like a big grain of sand, there is not a lot of room for surface reactions. But if you look at a clay, each one of these sheets, you see the small sheets that is happening here, each one of these small sheets is a surface of reaction, and it's full of charge in the soil. So this is the real important part of the properties of the soil that is conditioning the chemistry. It's a surface reaction between the soil colloids and the soil solution. So you have in soils primary minerals, yeah, simple silicates. Here are some examples, yeah, complex silicates. You have secondary minerals, which are weathered over time and changing over time. These are oxides, iron oxides, manganese oxides, aluminum oxides, not listed here also. Carbonates, yeah, magnesium and calcium carbonates, depending on how it's precipitated. And this is the one we want to call attention for these ones here, yeah. Silicate clays. The silicate clays are transformed over time, and they're layered minerals that possess a lot of charge, yeah. And there's a last one, which is organic, yeah. This is not minerals, but organic colloids also. So what is a colloid? What do you think is a colloid? How do you define a colloid? Have you heard that term before, colloid?
Yes.
What is a colloid? Huh?
The particles of the soil.
Yeah.
Before.
So they do not sediment, yeah? They do not settle on the bottom. When you did texture, you created a suspension of colloids that the clays were staying in suspension, whereas the sand and the silt were going to the bottom. You remember that. So you named the clays colloids. And the definition of a colloid is exactly that. Any substance that will form a stable suspension. It means that it will stay in the aqueous phase without going to the bottom, unless you apply a force, like you put it on the centrifuge and you spin it. As you spin it on the centrifuge, it will go to the bottom. So if you apply that force, you can separate it. It means it's not dissolved. If you can separate it, it's not dissolved, it's suspended. If it was dissolved like a salt, if you centrifuge it, it would not go to the bottom. But the clay will go to the bottom if you centrifuge it. Other examples of colloids you encounter every day. For example, milk. Milk is a colloid. Yeah? You leave it on the table, it will not settle. But if you centrifuge it, it will separate phases. Okay? Blood, if it's not coagulated, yeah, it's not. It will stay in suspension. But if you centrifuge it, you will separate phases. Anything that forms a stable suspension is a colloid. And in soil, all those small particles that are charged, yeah, all those small particles, they're very small, so they float around with any movement of the liquid, and they are charged, so they are hydrophilic, yeah, they have affinity for water. So these are the ones that will form the colloids. And we are concerned about colloids because of their properties. Now, what is a colloid? Yeah, extremely small, highly reactive organic or inorganic particles, electrically charged. Yeah. So why is this important? What do you think that the colloids being charged is an important thing for soil chemistry? How the colloid being charged is an important thing for the soil chemistry?
Because charging, if you're going or not going, coming or not going.
It's measure the concentration.
Concentration of
Ions.
ions will be attracted, yeah? If you have a colloid that has a negative charge, something with a positive charge will be attracted to that surface. So that the electrostatic interaction between any ion and the surface of a colloid makes the soil have a reaction, a surface reaction with the soil solution. It's attracting and retaining and making storage of nutrients, of elements in the soil. There are some elements which are constituent part of the minerals in the soil, and other minerals that are soluble, but they are adsorbed. It means they are attached to the surface of the particles. And they can only be
Also that heat it's attracting the water.
the water also, yes.
Between
Yeah.
looking at protein at hydraulic force.
Exactly. So all these reactions, they are not happening in gaseous phase. These reactions are happening in the aqueous phase. It has to happen between the solid phase and the interface with the soil solution. This all is happening in water, in the soil water. Never these reactions will happen if you do not have water. So all this chemistry is happening in aqueous phases. Yeah. So some of the properties of colloids. One, less than 2 micrometers in diameter. You remember that from the clays, yeah? They're very small particles, less than 2 micrometers. Too small to be seen with the light microscope. So you need to have an electron microscope to see it, like we seen in the first slide. That's an electron microscopy, scanning electron microscopy. Colloids have a large surface area. Because they are small, they have a lot of surface, and that allows it to have a huge amount of charge and a lot of reaction with the soil solution. So this is some measurements, 10 to 800 square meters per gram. When you measure in your samples, how much did you measure? How much was the amounts that you got in the lab? You did the AgMe adsorption, no? The monolayer of AgMe for surface area. You remember the lab that you did for surface area? You remember roughly the numbers that you get, how many square meters per gram? No? 1, 10, 20, 0.1.
What?
Surface area, when you did the labs. How much was the numbers that you got? Do you remember that? So, the more you have clays on your soil and the more you have organic matter, the higher you will get the surface area. The more you have clays, the more you have colloids, the higher you will get the surface area. If you add organic amendments like biochar, for example, or compost or anything to the soil, you expect immediately to increase the surface area of the soil. And if you have minerals, fine minerals like clays, you also expect to increase the surface area. 1 gram of sand will have 0.1 square meters per gram, yeah? Whereas if you go for clays, you can have up to 800 square meter per grams. So it increases by a lot. So you expect if this surface chemistry between the colloids in the solution is something that you consider important for the fertility of soils, then you need to have the more you can of this type of charges, yeah? Unless having too much clays will also damage other properties like infiltration rate and other things that will oxygenation, and maybe it will damage other properties of the soil. But you want to have as much charge as you can, because that means you can store more nutrients for the plants. It's a more fertile environment. So surface area means more charge, greater ability to hold water and nutrients. Yeah? So all these surface reactions is dependent on how much you have of surface area. Colloids are where these chemical reactions in soils happen. All these chemical reactions, in general, they are surface reactions with soil colloids. So the concept of surface area, you've seen already on the lab. If you fragment any particle, you expose more surfaces. If you split this on half, you will expose another face, and then you get more area. If you keep splitting this, you get more area. So the finer the particles are, the more area you will get of interface between these particles and the soil solution. Now, definition of clays. Yeah, you've seen definition of clays before on soil physics. All right, what is a clay? Huh? One of the soil separates, yeah, by size. How big is a clay? Below 0.02, yeah? or 2 micrometers, below 2 micrometers. So there are different ways of talking about clays. if you are talking about mineralogy, you're specifically meaning aluminum silicates. Many times when you talk about clays, you are specifically talking about aluminum silica and aluminum silicates. But as from the perspective of soil physics, we can talk about size fraction. Yeah? Any particle below 2 micrometers in diameter can be also defined, if you are in mineralogy, a group of minerals with specific chemical composition, as I was talking before. Or you can talk about a textural class. So when you classify a soil, maybe you're talking this is a clay soil. And you're classifying as a clay soil because you think it has an abundance of clay fraction. So, but it does not mean it does not have sand and silt. Also, it's just that the concentration of clay is high. So there are 3 ways of talking about clays. Yeah, here we're talking about the first one is the specific one that we are more concerned about the size fraction. Yeah. Clays are secondary minerals. Clays in soils are secondary minerals formed from the dissolution and alteration of primary minerals. Yeah? Depending on the type of primary minerals, depending on condition of the chemical weathering, then you will get different properties of these clays. And we must differentiate between 2 types of clays. Yeah? 2 types of clays. We have the crystalline aluminum silicates, and these crystalline aluminum silicates, they have 2 different broad categories of structure. Yeah, the aluminum silicates, they have sheets of tetrahedral sheets formed from aluminum and octahedral sheets formed from silica. Yeah, so you can have the tetrahedral sheet with 1 octahedral sheet, or you have 2 tetrahedral sheets with 1 octahedral sheet. These ones here are called 2-to-1 clays, and these ones are called 1-to-1 clay, because you have only 1 sheet to another sheet. Okay. These combinations of 3 sheets or 2 sheets, they can stack on each other and form layers. Yeah, and these layers can be multiplied many times, like a deck of cards. Yeah, imagine like a deck of cards. Each combination of TOT or TO can be 1 card, and then this card can have another card on top of each other. Let me see. We probably have some images here that will help. Yeah, Montmorillonite, 2-to-1 clays. Kyolenite, 1-to-1 clays. Elite, vermiculite, also 2-to-1 clays. In Oman, which ones do you think we have the most? 1-to-1 clays or 2-to-1 clays? Have you heard about this before? It's first time?
Yes.
Okay. We have in Oman much more 2-to-1 clays because soils are here are younger and more alkaline, so this tendency of forming more 2-to-1 clays. When the soils are more acid and older soils, more oxidized, you tend to form more 1-to-1 clays. So, the tetrahedron layer is a pyramid with triangular base, and silica is at the center of the pyramid, while oxygen are in the corners. Yeah, they are joined side by side. Here's what it looks like. This is the tetrahedron of silica, and they can bound sequentially side by side, forming a sheet. Yeah, a horizontal sheet, like a piece of paper like this. Yeah. Side by side they can join and they form a sheet like this. And this sheet can stack with other sheets forming 1 layer. Yeah? By the way, we can start taking attendance. So, octahedron is similar but with a different structure. Yeah? We have aluminum binding here in this manner with oxygen. And then also they can stack with each other forming sheets. Now, 1 layer of octahedra will link with another layer of tetrahedron. Silica and aluminum will stack with 2 sheets, one on top of each other. This is the structure of this aluminum silicates that I was talking about. Yeah, they stack to form a specific order, and 1-to-1 clays, TO, yeah, example kaolinite, 2-to-1 clays, TOT, example montmorillonite. All the smectite group of clays will be 2-to-1 clays, and the kaolinite will be 1-to-1 clays. In general, if you remember that, that's enough. Yeah, if I ask for you for an example or recognize an example, smectite, montmorillonite, 2-to-1 clays, kaolinite, 1-to-1 clays.
Victor, the letter TOT stands for what?
Tetrahedron, octahedron, tetrahedron. The sheets that you have from silica and aluminum, you will have, if you can stack one tetrahedron with one octahedron sheet, that is 1-to-1. If you stack two with one, that becomes 2-to-1. Yeah. So here, TOT, yeah, tetrahedron, octahedron, tetrahedron means you have 3 sheets stacked together to form one layer. Okay. Yeah, here will be a little bit more clear, maybe. Yeah, this is 1-to-1 clays, tetrahedral, octahedral. Okay, this forms 2 sheets, form one layer, and then you can have many layers stacked upon each other. This is 1-to-1 clays. Now you have many types of 2-to-1 clays that will be tetrahedral, octahedral, tetrahedral. In this manner, they can form one layer, and these layers can stack upon each other. Now, the important thing here, you can see the distance between these layers are much more variable than the 1-to-1 clay. When you have 2-to-1 clays, this layer here can be further apart from this one. Yeah, it means you can absorb more water and nutrients inside these layers of these 2-to-1 clays, unless they are packed with potassium like this, where they will be stacked close together. Yeah. The general case, take for just these 2 first ones here, yeah, the smectite and the kaolinite. Forget about these other ones here for the purposes of this course. Yeah. One of the other things is that you have to take in mind is, because you have this very close together and this can be farther apart, this type of clays, when you look in the microscope, they look very curly. Yeah, these smectite group clays, they are very curly. You can see that bending in shape, meaning like a round shapes, and where you see the ones which are 1-to-1, they look exactly like a stack of cards. They are very tightly packed, one on top of each other, and very horizontal. So if you go for the first slide, let me go back to the first slide, and I will show the microscopy again. Here, this is what it looks like 1-to-1 clays. You remember that I said they're tightly packed together in a horizontal manner. This is how it looks like on the microscope. Yeah, they're stacking very close together, very horizontal. And if I put on the web page here, smectite SEM microscopy, yeah, it will be, or maybe montmorillonite, images. They can be more curly. Yeah, they can be more curly, different. This is also not very good. Just a second here, let me find a good image to make my point. Like this, yeah? Like this one here. You will see that it's more like honeycomb style, more curvy. There is a lot more bending shapes when you have 2-to-1 clays. This is what you expect to find on a microscopy. Also with very high surface area. But each one of these is one of these layers with three sheets. Yeah, it forms shapes like this. It's not exactly horizontally back to each other, whereas in the case of the kaolinite, they will look more like this picture here on the right, where you have they're tightly packed to each other and very horizontal. So 221 clays, they tend to be more disordered in how they arrange themselves, and therefore you will have that they will be the more interlayer spaces, yeah, more interlayer spaces. So this is why on this image here, this is represented with more spaces here in between the layers of clay, because they arrange themselves in a more disordered way, and arranging themselves in a more disordered way, they can have more space, these micro environments where you have more space for water and nutrients to be occupying these interlayer spaces.
Doctor,
Okay?
that means 121 can't keep any water in it.
Yes, they can, but the spaces are more constant, so there's not a lot of space in between.
The smallest space.
Yeah, so in between the layers, there's not a lot of space. Yeah, but in this one here, there's more space in between the layers.
And the next one is little.
For now, these are all 221 clays, but for now, let's forget about the other ones. Just let's talk about the general case here, not the specific cases, okay? So you can even make a cross here. I will not ask about these on the exams, all right? I will ask about these two cases here, the 121 clay and the 221 clays. Because there is more flexibility, depending on whatever you fit inside here, depending on the ions that you fit, it will change how these sheets are shaping, yeah? And they can change the properties of the clays also. But I will not go into these details for now.
The exam.
And the exam, the first two ones. The first two ones, okay? The first two ones are the cases that I want you to.
Final and
The final also. Satisfied now?
yes.
Yeah, okay, exactly. Expect one question about this or more. Okay, now we know about the two types of clays, the aluminum silicates, and now we'll talk about how are they charged. How is it happen that the clay contains charge, on the surface of the clay contains charge? There's a phenomena that leads to that charge happening on the surface of the clays. And the first one is isomorphous substitution. Yeah? Isomorphous means same form, same size, same form, and substitution means something's being replaced by another one. Yeah. So it happens in highest abundance on 221 clays. Then it happens in 121 clays. And what does it mean is, in the structure of the clay, something will replace some ion will be replaced by another ion, and the valence of that ion will be different, and therefore the imbalance of charges will be reflected on the permanent charge. pH-dependent charge is the next type of charge. pH-dependent charge means that is a type of charge that is a surface hydroxyl on the clay. And if you change the pH, this hydroxyl can be protonated or deprotonated, generating positive or negative charge. I will explain this in more detail now. Yeah, this don't worry about in this slide. The next slides will explain better. Isomorphous substitution. Yeah, you have magnesium with valence 2. What happens if magnesium replaces the aluminum on the structure of the clay? Yeah, if magnesium substitutes aluminum, magnesium is +2, aluminum is +3. So there is lacking one positive charge. It means the clays have now one negative charge. But because this charge is inside the structure of the clay, it cannot make covalent bonds on the surface of the clay with another element. So if the phosphorus, for example, comes to absorb in the clay, it cannot make a covalent bond with this. It can only be attracted or repelled by this charge. Yeah. So any ion, any cation that interacts with permanent charge can only be attracted and there is electrostatic attraction, but it will not make covalent bonds. Yeah? On the other hand, if aluminum also substitutes silica, then it will create also a negative charge. Now, why would you think that this would happen? Why would you think that one ion will displace another ion and create this negative charge? What are the conditions that this should be happening? Why would you think this reaction would happen in the structure of the clay, something of the same size but does not have the right charge for that structure will substitute one another? Concentration, that is the answer. Yeah, that is exactly the answer. If you have in some history of the soil a condition where you have a lot of magnesium on the solution, just by the sheer gradient of concentration, some of that will be replacing. If you have in the history of the soil some condition where in the soil solution there is an excess of aluminum, then just by sheer gradient of concentration, they will substitute each other, and therefore generates the negative charge. Okay, so this is based on the long-term exposition of these minerals for varying soil conditions. If in some part, if these clays maybe have thousands of years, yeah, during those thousands of years, in some point of the history, there was a high concentration of another element on the solution, and they displace some of the one, and by doing that, they create a negative charge. Yeah. So in the tetrahedral layer, aluminium or iron substitutes silica. In the octahedral layer, iron, magnesium, zinc can substitute aluminium. So it always creates a negative charge. It's always, the permanent charge is always a negative charge. And that's why we called cation exchange capacity. Yeah, not anion exchange capacity. Also, there is anion exchange capacity, but the majority of the charge will be negative charge, and therefore cation exchange capacity is the property of the soils to hold those ions. Yeah, the charge that is created cannot be unbalanced. So in the soil solution, there must be always ions that were sticking to the surface of the clay by electrostatic interaction to compensate the charge in the clay. Never you can have this imbalance. So if you create a negative charge inside the clay, on the surface of the clay, you must have the ions that are compensating the charge.
Create a negative charge on the minerals.
Yeah. So the isomorphous substitution means inside that aluminum or silica sheets, the aluminum goes out, the silica goes out, and something else takes the place. You remember we have sheets of aluminum and silica on the aluminum silicates, okay? The aluminum or the silica can be knocked out of the structure and something else will take its place. If this happens and what takes place is something with lower valence, magnesium takes the place of aluminum, aluminum takes the place of silica,
Still positive.
but there is one less positive. On the whole structure, the number of oxygen stays the same, okay? The whole structure of the clay, the number of oxygen stays the same. Now you have one less positive charge. It means now you have an excess of one negative. The whole structure of the clay is not only composed of aluminum and silica. There's oxygen all across. You remember that? Here, the aluminum is surrounded by oxygen. This oxygen is giving the negative charge, okay? If you replace this oxygen or compensating the positive charge of the aluminum, if something with lower valence takes the place of the aluminum, it means you have one less positive charge. It means now the surface of this clay has a negative charge. It's unbalanced. Is that clear? Same things happens if you have the silica If the silica goes out and aluminum takes its place, silica plus 4, aluminum plus 3, you have an imbalance of one negative charge. So the clays have creates one negative charge. Why do we say this isomorphic substitution leads to a permanent charge? The permanent charge is something that is not affected by pH. Okay, so we talk about two types of charges. Yeah, isomorphic substitution, permanent charge.
Oxygen.
Question? No? Permanent charge, pH dependent charge. Yeah, if you change the pH, these charges will change. The amount of charge will change. The ones that are generated by isomorphic substitutions will not change if you change the pH of the soil. If you change the pH of the soil, the ones generated by isomorphic substitution will not change. Yeah, will not change. So these are the ions that can substitute each other in different sheets of the clays. Yeah, these are the different ions that can substitute each other and generate this imbalance. No need to memorize this, huh? For sure, no need to memorize this. Now, pH-dependent charge are the charges that if you change the solution, the pH of the solution of the soil, the amount of the charge will change. So, these are the type of charge that you find in organic matter, in iron oxides, yeah, overall. And also in silicate clays, but on the edges of the clay lattice. On the edges of the clay lattice, you will have these hydroxyls exposed, yeah. Imagine here, this is the edge of a structure of a clay. You have this oxygen bound to hydrogen. This is what we call a hydroxyl, okay? If it's just OH, there's no charge, all right? Imagine this, you have a clay sheet. On the edge of the clay sheet, you have the oxygen being with one hydrogen. So far, so good? What happens if you create more, sorry, what happens if you create more acid conditions? Acid conditions means more hydrogen, no?
Yes.
The pH is a measurement of the amount of hydrogen in the solution. So more acid conditions means more hydrogen. So hydrogen will protonate the surface of the clay. This protonation creates a positive charge. If you alkalinize the solution, there is less hydrogen on the solution. So the hydrogen that is on the hydroxyl will jump to the solution and deprotonate the structure. If you deprotonate the structure, you create a negative charge. If you protonate the structure, you create a positive charge. So this reaction here is the reaction which leads for pH-dependent charge. If you acidify, you get positive charges, and if you alkalinize, you get negative charges. In this point here, where it's uncharged, it's called the net zero charge or isoelectric point. Isoelectric point means the pH in which the clay does not have any charge. The balance of the pH-dependent charge is gone. There's no protonation or deprotonation, okay? How much did you guess this pH is? The pH where this has no charge.
7.
No? It will vary depending on the clay, but in general, approximately. Lower. Below, yeah, so normally below 4, even 4.5, it's very acid, yeah? This point here, where the clays are uncharged, this is an acid pH, which means that all the majority of the soils, they will be in this situation, where they are being deprotonated and therefore have negative charge. So pH-dependent charge is also negative charge. But the amount of charge will change if you change the pH. if you have more alkaline pHs, you have more negative charge. If you have less alkaline pH, you have less negative charge. But very rarely you get into this situation where you have positive charge being formed on the surface of the clay. So the isoelectric point is normally at a very acid pH. It will vary depending on the type of clay, or of organic matter also. But this is normally on the acid pHs. So if you over-acidify the soil below 4.5, let's say, you get positive charges. But the majority of the cases you have negative charge. But the more you increase the alkalinity, the more you increase the negative charge of the soil for this type of charges. Yeah, for this type of charges. So this happens in aluminum oxides, happens in iron oxides, it happens in organic matter, and happens in clays also, in the edge of the clays. Is this clear? I can explain again if you want. So always you expect, in Oman, how much is the pH of Oman soils? 7? Normally more than 7, 7.5, 8, 8.5, they are alkaline pHs. So you expect that you have a formation of high amount of pH-dependent charge, negative charges on the soils in Oman. Here is how is the sequence of formation of secondary minerals in the soils. And you can see here that there is first you get more formation of 2-to-1 clays. And with more chemical weathering, you will get the formation of 1-to-1 clays and oxides. The more mature the soil is, you will find more kaolinite and more iron and aluminum oxides. And the less mature you have the soil, you will have more 2-to-1 clays. Depending on the type of mineral and depending on the environmental conditions, you can get different types of 2-to-1 clays. But in general, you get 2-to-1 clays in younger soils. Sorry. Then you get in mature soils. The mature soils, you will have more kaolinite clays and iron and aluminum oxides. All right. So here is a table which I don't want you to memorize, but there is some information here that I want you to know. Okay? The information here is all these 2-to-1 clays, look at how much charge they have, the net charge. 80 to 150, 100 to minus 200 milliequivalent centimoles per kilogram, sorry. Now 1-to-1 clay, kaolinite. Yeah, very small, yeah, kaolinite 1 to 15. 2-to-1 clays tend to have a lot more charge than 1-to-1 clays. This makes them more useful for nutrient retention and soil fertility. Now, allophonimogolite or volcanic type of clays, volcanic clays, yeah? There are also aluminum oxides, but these also, they tend to have a lot of charge also. But the one that wins all the competition here is the last one. 100 to 500. Comparing to all the others, it has a lot more charge. So it means that if you're looking to increase nutrient retention on the soil and fertility, the organic materials are the ones which are the best candidates. Also, for you to add in the soil, organic matter is a common type of amendment that you can add compost, you can add biochar, you can add a lot of different types of organic materials. But if you want to add clays, it's not so easy for you to find and add clays to the soil. So comparatively, 2-to-1 clays have more charge than 1-to-1 clays. And organic matter, organic humus, the colloids, organic colloids, they have more charge than any type of clays that you can find in the soil, which are mineral clays. Yeah?
Read the organic color.
Humus or organic colloids, they will have much more charge than any mineral clay. The organic colloids will have more charge than any mineral clay. All of it is pH dependent. All of it. Yeah? There's no isomorphic substitution in organic colloids. All of the charge from organic colloids, it's pH dependent. In the clays, it will vary. You may have some, the majority must be isomorphic substitution, but some of it will be also pH dependent. Within the mineral colloids, 2-to-1 clays have more charge in general than 1-to-1 clays. So this is what I want you to know from this table. Not memorize the numbers. 2-to-1 clays have more charge than 1-to-1 clays. Organic colloids have more charge than any mineral clay. Clear? Check time. I think we leave here for today and we continue next week.